そうしましたら、続きまして、ジョージ・ワシントン大学のプロフェッサー・ネーゲルからローエナジー・ニュークリア・リアクション・ロバスト・リザルト・プロミシング・ポテンシャル・クリティカル・チャレンジという題名でご講演をしていただきます。
Good afternoon. It is a pleasure and a privilege and an honor to be on the same program with Professor Kasagi and Professor Iwabura. These are two remarkable scientists. If you don't know them already, you should learn what they have done. Remarkable experiments, and they found very, very interesting results that are not understood now, that challenge our theoretical physics. So I am more than pleased to be here with them. So the talk that I will give is about low-energy nuclear reactions. And it says here, robust results, promising potential, and critical challenges. This means that we have a very solid experimental database now for the existence of the ability to produce nuclear reactions using chemical energies. A controversial statement, and if you're in doubt about this, if you're curious about this, I implore you to read the literature. There are a few thousand pages. I think you'll find a lot of data, and some of it is, you can't make it go away. Promising potential. Will this solve the world's energy problems? No. Will it contribute to a solution? Yes. How soon it will is an issue, and I'll come back to that. Many, many challenges remain, so that's where the critical challenges come in. Now let's see if I can work this. To put things in context, especially for those of you who are not familiar with the field, I have to start talking about two things, terminology and the two branches in the field. These are names that have been applied to this field over the years by individuals and by companies. Okay? And one of the reasons it's difficult to keep track of things in this area is because we don't understand the fundamental physics of it, and we don't know what to call it. So people call it all different kinds of things. I personally prefer lattice-enabled nuclear reactions. It's specific. Low energy is a relative term. It's not as clear as it should be in my view. Still call it LENR, which is a recognized acronym in the field now. The terminology used here, condensed matter nuclear reactions, the division here at Tohoku is bang on. It is exactly what is important and is going to be studied. The other preparatory thing I have to say is that the field has two branches. You've got some of that in the talk you just heard from Professor Kasagi. The original approach by the two people who started this, Fleischmann and Pons, was the electrochemical loading of deuteriums into deuterons into palladium. The temperature is limited due to the boiling of the light or heavy water, and it's now primarily of scientific interest, at least for the near term. By contrast, gas loading of protons into nickel started very early also. Temperatures above 1000 C are being used, good for electricity production, and it is the basis for the first commercial LENR generators, almost without a doubt. So with that background, I give you an outline for the talk. I'm going to spend a couple of graphs on the energy context. This is the bulk of the presentation, okay? And my expectation is I'll have relatively little time to talk about this, but I want to present you a little data teaser, if you will, about some of the things that are in fact available in the literature, and then I have a brief conclusion. So what's the energy context? This is a plot of energy flow in the United States in the units of quads, quadrillion British thermal units. Okay, here. This is where the energy comes from. This is how it's used, where it goes, electricity production, and so forth. And since this number is about 100, these are roughly percentages. The black bars indicate the fossil fuels, coal, and petroleum and natural gas. And the green are the alternative energies and so forth. And you see the boxes aren't proportional in size. This is 35 units and this is 2.56 units. But nevertheless, you can take a diagram like this, follow it through, look at how much goes into electricity generation, and then where it goes. There's electric cars come down here. Okay, that'll increase in the future years and so forth. So this is a snapshot of the situation in the United States. A similar picture for Japan is shown here, and it's different, but it's similar in that fossil fuels still are the dominant sources. lots of electricity production, needs uses. And I didn't say in the last graph, but it's true here. These units are petajoules, okay? The units are different, but it doesn't matter. What actually gets used is 7,500, but what gets rejected due to Carnot inefficiencies and bad insulation and friction and various losses is far more than what gets used. So energy conservation is a serious possibility, but it isn't going to, even if you shave this down, move some of this into this, save the day. The situation for Japan, of course, is that it's heavily dependent on imports, and I salute you, Mr. Yoshino, for a broadband program ranging from the academics that are going to be pursued here at the university all the way through to your companies, and we all hope indeed for a clean planet in future years. Okay, so let me get to the meat of the talk. It's going to be on the science, the engineering, business, and education of LENR. This you all know, but it's useful. Science provides knowledge and opportunities to engineering, prototypes and products, feeds back money, and so forth, and then education spans all of it. All four of these areas are very active in LENR right now, okay? The educational opportunities are very serious, and I understand there's some students in the room. If you want to have some fun, consider studying this area, okay? It is challenging on many levels, all of these levels, scientific, engineering, and business. So what I've done is take those three things and use them as a template to discuss the three dualities for LENR: experimental and theoretical under science, experiments and prototypes of products under engineering, and then the two kinds of companies involved in the field, little ones and big ones. Okay, so what I'll do in this following view graphs is show you a couple things here, a couple things here, and so forth, in order to attempt to give you the big picture as far as this area of science and technology is concerned. Okay, so let's start with experimental science. Thousands of LENR experiments performed by competent researchers, hundreds of reports of the observation of excess heat. Energy gains exceeding 25 have been reported for the palladium deuterium system, and gains over 400 have been reported for the nickel hydrogen system, not adequately verified. Okay, so you can say it's like a supernova. It goes off, but you can't do it again. You can't control it. Nevertheless, it went off. Transmutation products have been reported many times, correlated with heat production a few times. Okay, so it's a real problem if you're new to this field to get your arms around it. Okay, but nevertheless, it is possible, and if anybody wants to consider it, I'd be happy to talk to them. Now, this is a graph I shouldn't show you because it's too complex. It violates various rules, but it's really, really important. It's from Schwartz, a researcher in the Boston area in the United States. So let me walk you through this. This is time horizontally, 15 hours. Power plotted on the left in milliwatts, so this is like a cell phone power somewhere in there. And the integral of the power, namely the energy, plotted on the right. And there are two curves for two experiments. So you have two experiments, a controlled and an active experiment, current going through them like this. And he determined the input electrical power and the output thermal power on each one of them. Okay, so let's look at the control first. The experiment was turned on. A short time afterwards, the calorimeter responded. The two ran together. These are the integrals that came up to the same. He knows how to measure energy, input and output. Okay, so now let's look at his active experiment. Here's the power into what he calls a fuser, and it comes running along like this. But look at the power out. It exceeds the power in, and runs consistently higher, so that when you integrate the power in, it looks like this. The integration of the power out looks like this. And this is the excess power, the additional power that's been produced, the excess energy that's been produced during this experiment. Then he turns the experiment off, and it keeps producing power. It's so-called HAD, heat after death it's called. And you get a little additional increment of power. So I show this, despite its complexity, to show that there have been very, very careful experiments done by competent people who know how to measure energy and still see very, very important values. Okay, so I could show you many more of these. I'll touch on a few later if I have the time, but I don't think I will. Okay, so let's turn to the theoretical situation. About 36 theories put forward by accomplished physicists. I mean, people who have the credentials to consider the theory that's necessary to explain this. None of these theories is fully developed, predictive and tested. None is widely accepted. And to make things worse, there are some single-step nuclear reaction theories, but there are some two-step theories also that say, hey, it isn't as simple as just one nuclear reaction. I don't have time to go into it, but the situation on the theoretical side is, it's a mess, okay? And that's not a knock on the theoreticians. They are trying very hard to make this going. So what do we have here? This is a summary of the theoretical talks that were presented at a conference I hosted in Washington in 2008. These are the 22 theoretical papers that were presented, and then we attempted to categorize them. Okay, now of course I can't go into this, okay? If I tried to, you should run out the door. It's too complex, okay? But nevertheless, I'd like to illustrate to you that there has been a tremendous amount of theoretical work that is so far unacceptable. So some bright student sitting in an audience like this says, ha, there's a chance for me to get famous, if not rich, okay? There's hope. Okay, turning to the engineering side, experiments have been well designed. We've been under attack for over a quarter of a century by competent critics that we don't know how to make measurements. We have learned how to make measurements, okay? There's no question about that. Power measurements down to the milliwatt level have been made. Chemical analyses for transportation products have been made. Many measurements are made redundant sensors, and there are several obvious opportunities for even more work to be done. Okay, so these are pictures that I chose. The top two are from a private laboratory in New Mexico in the US. This is the experiment that Professor Iwamura and Ito-san here had at the Spring 8 here in Japan. This is a photograph of a laboratory, an academic laboratory, the Institute for Nuclear Renaissance, they call it, in Missouri in the United States. Okay, so we think there have been some well-designed experiments. What about the prototypes of products? They're being developed by some LENR startups, and they've sometimes been quite simple. Part of it's due to lack of funding, and some of it's due to rushing to get to market. The best funded LENR development company has a relatively sophisticated engineering. They should have. They have had $70 million of investment so far. Okay, Blacklight Power in Pennsylvania in the US. And there are many, many tools that can be used to design experiments, design prototypes on this book. So these are examples of prototypes of products. So this is from Rossi. On the top here, these are from the Greek company Decalion. I took these pictures when I worked in their laboratory in 2012. And these prototypes wouldn't run but a few hours before they would self-destruct, okay? Not from LENR, they just didn't work, they weren't well engineered. So anyway, the situation on engineering is that experiments are much, much better engineered than the prototypes of products so far. Now turning to business, there are some small companies devoted to developing LENR power commercially. There are a few dozen of them, but 5 of them get most attention. They're listed here. I won't go through them, except to note that one of them, Industrial Heat, recently acquired the rights to technologies developed by Andrea Rossi, and they are working to develop currently a megawatt generator, and then later, smaller kilowatt generators for use in the industry. That's why they call it industrial heat. And then even later, home heaters and things like this. Okay, so this is one of the startups that's well worth paying attention to. Now, big companies are watching. I had a commercial short course on LENR in 2011. GE and Lockheed Martin came. Royal Dutch Shell and the large Norwegian oil company Statoil have an interest in LENR. MHI and Toyota here, I have a research program. It's the big electronics company in Europe. ST Microelectronics has had an interest in this for many years. National Instruments, a $1 billion instrumentation company in the US, is looking at this. The Swedish consortium of energy companies is supporting testing. Airbus has an interest in it now. It goes on and on. Okay, there is a lot of interest on the part of large companies. So 2 of us, Steve Kadinsky, a successful businessman from Los Angeles, and I, in the last month, formed an industrial association for LENR. Industrial associations are like the glue that hold together an industry, okay, pre-competitive technologies, if you will. So we're in the process now of standing this up. The website just became active, and if you want to know more about that, go to our website and learn more about it. Okay, so that's the large picture. Okay, if you have any questions, I'd be happy to answer them, any comments, but now they can go on now. So let me show you some data. Okay, experimental evidence. I know how to do it. Sorry. Experimental evidence of two types, nuclear products and thermal energy. This is very, very compelling from a practical viewpoint, from a commercial viewpoint, but there is some very, very good data available here, which I'll show you in the following view graphs. Now, in order to sort of keep your head straight in this business, it's good to classify things about how the experiments are done. That is, how are either protons or deuterons brought together with metals or alloys. They can originate from liquids in electrochemical experiments, gases, thermodynamic experiments, plasmas, or beams. And then what comes out? Excess heat, nuclear products, other things. So fundamentally, what I'm going to do is talk a little bit about this column, and then a little bit about that, okay? Now, an organization for the experimental evidence is shown here. Nuclear products, you have elements across the periodic table, and then specific elements that have been measured in the experiments by Iwamura-san and others, and then the production of helium and tritium. So I'll show you examples of 1, 2, 3, and then I'll turn to the thermal energy. Now this is a very complex graphic. It shows data from 2 papers, 1996, one from Illinois, nuclear transmutations in thin film nickel coatings undergoing electrolysis. Okay, and the other is from Dr. Mizuno, who's here. Raise your hand, please, if you don't know him. Isotopic changes of reaction products induced by cathodic electrolysis of palladium. So in both cases, horizontally, you have atomic mass from 1 to 250. These are lined up. And vertically is, in this case, the production rate. Atoms produced in an experiment per cubic centimeter of the material per second. Absolute numbers. They measured how much was in the experiment before and how much was in the experiment after, and by difference, they plotted these. Now, Dr. Mizuno has different units here. These are the counts in the mass spectrum. But the point of showing this is that there are peaks in these spectra. These are log scales, you notice? Look at the variation, the orders of magnitude. And the peaks line up. And I remember the feeling when I first saw this data. I think this was presented first, was it not? And then you did this. And I remembered the peaks here, and I said, they're the same peaks. It was one of the exciting parts of my time at a conference and as a scientist, that verification. So here are 2 widely different experiments. Different materials, different techniques, and they give the same answer. You can produce elements across the periodic table, and they agree with each other. So a fellow in Switzerland and I did a statistical analysis to answer quantitatively, do these really correlate with each other? And the answer is emphatically yes. It verifies our eyeballs, if you will. Okay? So this is production of elements across the periodic table. Let me turn next to the production of helium. So horizontally is the increase of helium, parts per million per volume, okay? In an experiment that was done at SRI International, Professor Kasagi already mentioned Mikamine, and that's plotted vertically against the estimated energy in kilojoules from the same experiment. There are 2 different methods of data analysis, but they tell the same story. They correlate, okay? You get helium atom, there's so much energy associated with it. Now, somebody in the back says, how many times has this been done? The answer is 16. 16 different experiments. People have measured quantitatively the helium and the heat and found a correlation. And they pretty much agree with each other. There's a distribution, some spread, some scatter, which is normal. But it's a remarkable situation that A, you can make helium, B, you can make heat, and they're correlated with each other. Okay? So now going on to tritium production, this was an experiment done by Claytor and his colleagues at Los Alamos. It was a plasma loading experiment. They had a glow discharge in this chamber with a palladium wire there, and then they had gas flowing through the system. So it would come out of the experiment here, come around here, through a tritium gauge. Okay, so you could plot tritium concentration, nanocuries per liter vertically versus time this way. And sometimes they didn't get anything, okay? No tritium production, but sometimes they did get. Look at the signal to noise. This is a very high signal to noise. Up here, the noise is that big, the signal's that big. So it's not a marginal experiment in terms of the data. Oh, and then afterwards, they burned the gas and subjected it to a different kind of measurement and got the same answer. Okay, so there were two techniques used to measure the tritium. And you see that in some cases, when they did things like turning the plasma on and off, it responded. Was this controlled? No. Fully controlled? No. Was it understood? Heavens no. Nowhere near understood. Okay, but you can make a very interesting material. Tritium, as most of you know, is radioactive, has a short half-life, does not occur in high concentrations in nature, and here you can measure it with great sensitivity in a laboratory experiment. Okay, so you say, I don't care about nuclear transportation. Show me the heat. Okay. Here's the heat. This you saw already. It's a plot from a company in Israel. Time goes horizontally here. This is 15 and a half hours. This is power in watts, 0 watts up to 40 watts. They have an experiment running. This is the input power measured electrically, and the output power measured by a calorimeter takes off. And then the ratio, if you just simply take the thermal and divide it by the electrical, is 26. Has this been verified? Yes. A joint experiment between an Italian government lab, ENEA, and the Stanford Research International redid this experiment, and the energy gain they got was 70. It was better than initially reported. Okay? Astounding. The questions of reproducibility in this field are still very vexing, very important. We don't know how to do experiments the same time after time after time because of some unknown aspect of materials, let alone our lack of understanding. But sometimes when an experiment is redone, some very spectacular results are available. Now turning to some gas loading of nickel with hydrogen, Rossi and his colleagues in the time frame indicated here did experiments of durations of an hour, 53 days.